Dirtman here with another special report. I've got something really cool going on right back here, but it's gonna have to wait for spring because it's snowing. So today I'm gonna head back inside and I'm gonna do something really cool that you may not have seen before with light and crystals.
I've come inside, I'm all warmed up, and I'm here with geochemist Dr. Kyle Trossel.
Howdy.
And today, we are going to look at the structure of crystals. Most people, when they're looking at the crystal structure, they're looking at how perfect it is, double terminated, or even twinned, like this Japanese twin here. We are going to go inside the crystal using polarized light, and it's going to look much different than what you think.
One of the most beautiful and useful of minerals is rock crystal or quartz. Once used principally for decoration, it is today more than a thing of beauty. The quartz is submerged in oil so that the optic axis may be located and marked. The optic axis is found by locating certain bands of color which are formed when the quartz is examined in polarized light.
First, we start with a light board, like this one, that you can get on eBay or Amazon.
So then we'll add on a linear polarizer. You can think of light as a wave, and what this linear polarizer is doing is it's letting us only see one direction of that wave. So here we have a tourmaline crystal. With our plain polarized light, we'll be able to identify pleochroism in our tourmaline. This is an optical property that can help us to identify unknown minerals. So right now, you can see a light green color with our tourmaline. As we rotate the tourmaline 90 degrees, you'll see that it goes dark. So this is pleochroism, a change in color as we view our mineral specimen with plain polarized light. This is one of the first things we can do with our polariscope setup. So the next piece of our polariscope is going to add in an additional linear polarizer. And with this, what we're going to see is not very much. So our new linear polarizer is basically blocking out the light that is vibrating in a single plane since I put it at 90 degrees to our original polarizer. But if we have a crystalline mineral in between our two polarizers, some pretty awesome things are going to happen.
First, we're going to add a citrine quartz crystal.
Now we bring in the upper polarizer again, and you can see in this orientation, it's not really letting much light through. However, as soon as we rotate it, you'll see it starts to transmit light. This is letting us know that our quartz is anisotropic, a fancy word meaning it's different in different directions. Also note that the directions of our crystal go dark and light with respect to the directions of our linear polarizers. So this is telling us something about the structure of our mineral.
Also, in polarized light, certain types of imperfections in quartz are revealed by other patterns in color. The triangular patterns indicate twinning of the quartz. Twinning is an imperfection which must be discovered and twinned regions avoided in the finished plates.
So we can also use our polariscope to investigate the structure of our quartz crystals and twinning.
For this experiment, we are going to use Mohawk diamonds from Mohawk Valley Mineral Mining in New York from the Herkimer Mining District that have been prepared by slicing them into sections and polishing them. This allows us to look down what's called the C-axis, which would usually have the points at the ends.
We are currently viewing these in plain polarized light. We'll bring in our upper polarizer and you'll be able to see all sorts of fun going on. What we're seeing here is a combination of the optical activity in quartz along with Brazil law twinning. That's why we're getting all these cool colors and geometric patterns. The geometric patterns are actually those Brazil law twins.
So when you think of Herkimer diamonds and being water clears, we call them perfect. What this is actually showing us, the Brazil law twinning is an imperfection in the crystal structure. This is a great example of how optics can be used to see things you can't see with your naked eye. Now, let's compare these to other types of quartz crystals from a different location.
Here we have another rock crystal slice, and we can see it has very limited Brazil law twinning. Here's a citrine slice. This one has almost no Brazil law twinning. Here we have a smoky quartz slice. This one will have more significant Brazil law twinning, sort of more similar to our Herkimers. And then the last one is amethyst, which is actually going to be kind of special. It has Brazil law twinning that is polysynthetic. So this is going to look like a crazy menagerie of colors and triangles. You can see on the spectrum of Brazil law twinning, our Mohawk diamonds are actually a bit closer, probably towards the amethyst than to some of the other slices we have here.
So here we have an almost perfect water clear Mohawk diamond. Let's see what happens using these techniques looking down the A-axis, a different side of the crystal.
So here we have our upper polarizer, and you can see as we rotate it, very similar to our citrine before, it transmits light, then it goes extinct at very specific angles. This lets me know that is indeed quartz. We have another trick we can do with our polariscope setup, and this requires an additional lens to be brought in to our setup. And what this will let us do is generate something called an interference figure. So when I get this situated just right, this is going to tell us actually about the symmetry of our crystals, and it's also going to tell us about the twinning. So if you see in our very twinned amethyst, that figure is all sorts messed up. If we take a look at our less twinned citrine, you see a nice circle in the center there. This is telling me that this is quartz in particular. This is a result of a property called optical activity.
So taking that principle one step farther, now we're going to get really trippy and go psychedelic. So again, with our double polarizers,
we'll bring in actually a sheet of muscovite mica in between them, and you should be able to see some pretty trippy colors. So what you're seeing here with these interference colors and the pattern that they're generating as we rotate this muscovite crystal in different planes, you're seeing part of a BXA interference figure. As we move in different orientations, you're sort of moving around in space. This is actually a result of the crystalline structure of our muscovite, and it's telling us our muscovite is something known as biaxial.
this has been absolutely amazing. I have never seen anything like this before today. Thank you, Dr. Kyle Trossel. This is just absolutely spectacular.
Well, thank you, and also thank the minerals because they're very awesome.
To learn more about polarized light, polariscope setups, and educational mineral specimens, check out Snellius Minerals on eBay and YouTube.
Dirtman here, bringing the geology to you with Dr. Kyle Trossel here in York County. Back to you, Jerry.